Hi everybody! So in today's video we're going to be learning about Unit 2 Lesson 8, which is about something called the limit definition of the derivative. So we have 3 learning targets for today. Learning target number 1 is I can represent the derivative of a function at a specific point using limits. So we're going to be representing the derivative, so showing it, in a new way today using limits, which we learned in Unit 1. The second learning target for today is I can represent the general derivative formula for a function. So we're looking now at kind of a general, we're going to take the derivative and get an equation using limits. Whereas I probably should have highlighted that the first part here was at a specific point and the second one is for a general formula. And the third learning target is I can recognize when an expression represents the limit definition of the derivative. So you need to know it when you see it. Recognize when an expression represents the limit definition of the derivative. And use a derivative to find the value of that limit. So once you know that that limit is really a derivative, you can just use derivatives to find the value, which is what we're going to learn how to do today. So let's start with this. In this unit, we've learned how to find the derivative of a function using a variety of derivative rules. Now we're going to investigate where those shortcuts came from and the connection between derivatives and limits. So now that we know all these rules, they're not magic. They didn't come to somebody in a dream. What these are rules that have been developed over time by using limits to find derivatives. And we're going to kind of work through how to use limits to do that today. The following limit can be used to find a general formula for a derivative. Now, when I say a general formula for a derivative, I mean that if f of x is equal to 3x squared plus 7x minus 1, the general derivative formula would be 6x plus 7. And the reason we call this the general formula is because we didn't plug in a specific x value here. We could use this formula and plug in whatever x we want to get derivatives, but we haven't done that step yet. So this is the general derivative, and then if we did plug in a number, that would be the derivative at a specific value. Here's how we can use limits to do this. I want you to imagine that we're trying to find the slope of a line. In this case, though, we're going to give the points on the line special names. So on this graph, we're going to think about the first point as being the place where the x coordinate is x, and the y coordinate of that point would be f of x. Now, if we imagine sliding over a little bit, so h is just the distance we slid over, so maybe we slid over 1 space or 2 spaces. Now, the second point that we're working with here, and I should have put another parentheses here, I apologize. The second point that we're working with here is going to be this point up here, which is the point where the x coordinate would be x plus h. So our original x plus however much we slid over. So x plus 1 or x plus 2. And our y coordinate then on the graph would be f of x plus h. So whatever we get by plugging in that new x. If we were to write the slope of this line using those 2 points, then that slope would be y2 minus y1 and x2 minus x1. So the formula would look like this. F of x plus h minus f of x, so y2 minus y1, all over x2, which in this case is x plus h, minus x1, which in this case is x. So I'm just doing general, regular old slope because we're going to find a derivative is a slope. So we're finding a slope between 2 points. Now we can simplify this a little bit because on the bottom here, this x and this x will simplify and make a 0 pair. So x minus x makes 0, which means that my new simplified slope would be f of x plus h minus f of x all over just h on the bottom. Now that's how we would find the slope between these 2 points. But what made derivatives slopes special was that we wanted the slope at 1 point. So what we're going to do here is we're going to take this equation we just came up with, and we're going to find the limit as h approaches 0. Now let's think about what that means. H is the distance between the 2 points. So by finding this limit, what we're really finding is what happens to the slope as the 2 points move closer together. So that's what that limit does, is it takes a slope that uses 2 points and it slides them closer together. It's making the distance between them become 0. And by sliding those points closer together, we take what used to be a regular old slope and we turn it into the derivative, a special slope, where the distance between the points is 0. Now, if we wanted to use this limit definition to find the derivative if f of x is equal to x squared plus 2, let's think about how we would do this. This formula right here is what we call the limit definition of the derivative. So this is a really important formula because this tells us where our derivative formulas came from. And we're going to show you how that works right now. So how could you use this formula to actually find the derivative? Now, in my mind, I know that if f of x is x squared plus 2, then the derivative should just be 2x. I know that. So in order to actually find that, we can use this kind of limit to verify that that's correct. Here's how we would do that. I'm going to start by writing down the formula. The formula is limit as h approaches 0 of f of x plus h minus f of x all over h. Now, in order to do this, we're going to need to be specific about our particular f of x. So if we go back to the directions, f of x here was x squared plus 2. So if I make this specific to my problem, I'm going to have the limit as h approaches 0. And then step 1 would be to find f of x plus h. That's kind of like step 1 of this formula. What that means is take the x plus h and plug it into your x squared plus 2. So I'm going to have, instead of x squared plus 2, I'm going to have x plus h squared plus 2. Because if this says f of x plus h, it means replace the x with x plus h. Minus, then it just says f of x, and f of x is just the original formula. So this step right here, where it just says f of x, would just be copying down the original formula again. So x squared plus 2 all over h. Now we're going to simplify this fraction. In order to evaluate this limit, you would need to plug in h equals 0, but unfortunately in this case, if you try to plug in h equals 0, you're going to get 0 over 0. So we're going to need to simplify this a little bit in order to actually evaluate it. Step 1 of the simplifying is to multiply out x plus h times another x plus h. So I'm going to multiply that out by distributing. When I distribute here, I get x squared plus x times h plus x times h plus h squared. And that's kind of just what used to be the pink part right here, plus 2. And then I'm going to go ahead and distribute this negative. So I would have negative x squared minus 2 all over h. So I just distributed the negative here. Then we can simplify again. So x squared minus x squared, they simplify out and make 0. Plus 2 and minus 2 simplifies to make 0, which means my new simplified limit would be the limit as h approaches 0 of 2xh, because I have 2 xh's, plus h squared divided by h. Now, we still can't plug in h equals 0, because if we do that, we get 0 over 0. But on the top, we can factor out an h. So we would get 2x plus h over h, and h divided by h makes 1. So now we just have the limit as h approaches 0 of 2x plus h, which means now we can plug in h equals 0 and we just get 2x. Now, the nice thing is, since we know our shortcuts, we never have to find derivatives this way. You're never going to have to really work out this formula for yourself, but I did want to show you where some of those shortcut rules that we learned come from. They come from using this type of a limit to actually slide 2 points closer together and to then get your derivative formula. Option number 2 would be to find the derivative at a specific number. So this time, instead of just calling our point x and x plus h, we're going to call it a and a plus h. So the first point here would be a and f of a plus a, or f of a. And the second point here would be a plus h and f of a plus h. And so if you wanted to find the derivative this time, your new formula would be the limit as h approaches 0, because again, we want to slide those points close together, of f of a plus h minus f of a all over h. An example of how this might look would be that you might see a limit written like this: the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h, in which case you know that you were finding the derivative at x equals 2. Because the a here was replaced with the number 2. The last way that you might see a limit used to find the derivative is you might see a limit used like this. Instead of just calling it a and a plus h, we're just going to call it a and some random x. Now in this case, we're going to set up our slope formula. So our first point here is a and f of a, and our second point here is x and f of x. So our slope formula would be f of x minus f of a all over x minus a. But this time, instead of letting h approach 0, we're not kind of using h to represent the distance. In this case, we just want this random x that we chose to slide closer to a. So our limit would be the limit as x approaches a. An example of how this might look if you were to see it set up in a problem is the limit as x approaches 2 of f of x minus f of 2 all over x minus 2. Now, we could use the limit definition to find g prime of 3 if g of x is equal to x squared plus 2x. So we're going to choose one of these two options, either this option, which is our second way of representing a limit, or this option, which is our third way of representing a limit, a derivative using a limit. And I usually like to use this one when I can because it's just a little bit simpler. So my general formula that I'm going to use here is the limit as x approaches a of f of x minus f of a all over x minus a. In this case, my a is going to turn into a 3 because I'm asked to find g prime of 3. And I'm going to also need to use my specific formula g of x. So I would have the limit as x approaches 3, and I would use my function. So instead of f of x, I'm going to use g of x here. So that would be just your formula without any numbers plugged in. So that would be x squared plus 2x minus, now instead of f of 3, I would just take the number 3 and plug it into g of x. So this means plug the number 3 into your actual g of x function. And if you do that, you get 9 plus 6, which is 15. So you'd have minus 15 all over x minus that x that you plugged in, which was 3. Now, again, we're going to need to simplify. If you try to plug in the number 3 right now, you get 0 over 0, which is not an option. And so we are going to simplify this by factoring. So my simplified function here would be x squared plus 2x minus 15. And when we first learned about limits, we said if you see a problem like this and you try plugging your number, you get 0 over 0, try factoring. So if I factor the numerator, I would get x plus 5 times x minus 3 divided by x minus 3. This factor and this factor, since you're dividing by the same thing, you get 1, which means that they simplify. And so we get the limit as x approaches 3 of x plus 5. And now we can actually plug in our number 3, which gives us 8. Now, if we wanted to try this using the shortcut rules, just to check our answer, we could say the derivative of g of x would be 2x plus 2. And if we plug in the number 3, we would get 6 plus 2, which is 8. So you're still finding the derivative using just a different method. Now you might be wondering, why go through all this work? Why use these limits to find a derivative if we know we have shortcuts? And the answer is we don't ever really find derivatives this way, but we do need to recognize it when we see it. Oftentimes, you'll be required to recognize the limit definition of the derivative in order to answer a question. The key idea here is that you do not need to evaluate the limit algebraically. Once you know that a limit represents a derivative, you can use shortcuts to find the answer. They are faster. So each of the following limits represents the derivative of a function. We want you to do 3 things. Identify the original function. So what equation do we need to take the derivative of? And the x value at which you are calculating the derivative, if applicable. So if it is at a specific number, what is the specific number? And then use shortcuts to actually solve the problem. So here's what we need to do. We don't ever need to really evaluate these limits because let's say I look at problem A here. The first clue that this is a limit that represents a derivative is that this is the limit as h approaches 0. So that's clue number 1, that this is a limit that represents a derivative. If that's the limit that represents the derivative, then that tells me that I probably used this formula right here, the limit as h approaches 0 of f of x plus h minus f of x. Now, when I use that formula, I would expect sometimes there's going to be x's and sometimes there's going to be numbers plugged in, like we saw here. In this example, this is going to be a situation where there's a number plugged in. Do you see here at the beginning? If we think about this as f of x plus h, the x would have to be 4. So that's the specific number that was plugged in. Now that x plus h in this case was plugged into the square root function. So it tells me that the original function, f of x, is going to be the square root of x. And that the x value where I'm trying to find the derivative is just going to be 4. Now, I can actually do this problem using shortcuts. I don't need to evaluate the limit. If you try to plug in 0, you're going to find you get 0 over 0. There's nothing to factor. It doesn't work. So instead, I would take the derivative using my shortcuts, which is going to be 1/2 x to the negative 1/2, or in other words, 1 over 2 times the square root of x. And then I would plug in the number 4, which would be 1 over 2 times the square root of 4, which is 1 over 4. So 1/4 is the answer to this limit because this limit really means take the derivative of the square root of x at 4. Problem B is similar. My clue that this is going to be a limit that represents a derivative is that this is h approaches 0. Whenever you see that, this is probably a limit that represents a derivative. Now, just like we saw in the previous problem, the beginning of this limit is f of x plus h, which tells me that my f of x function was the sine function, because that's kind of the outside of this pi over 2 plus h, and that the specific x value I was trying to use here was pi over 2. So if I take the derivative now using my shortcut rules, which makes my life a little bit easier rather than trying to evaluate a limit, the derivative of sine would just be cosine, which means the derivative at pi over 2 would be the cosine of pi over 2, which is just 0. And I know that from using my unit circle. When you're standing at the pi over 2, the x-coordinate is 0. And this is going to be the answer to this limit, because that is a limit that really means the derivative at pi over 2. For part C, again, my clue that this is going to be a limit that represents a derivative is that h is approaching 0. So I'm going to look at kind of that first term to figure out what's happening here. It looks like my f of x function is going to be natural log. And in this case, there's no specific number that was plugged in. And the reason that there's no specific number is that this is still an x, it's not a number. So what this is meaning is just take the derivative without a number plugged in. So the derivative would be just 1 over x. And that would be the answer if you simplify this limit, because this limit really just means find the derivative for any x. For part D here, it looks like this is going to be another limit that represents a derivative. And my number one clue here is that this is the limit as h approaches 0, which tells me this is probably a limit that represents a derivative. If I look at the beginning of this fraction, if I think about that as f of x plus h, it looks like my f of x function is going to be e to the x. And it looks like I'm being asked to plug in the specific x value of 2. So my derivative of e to the x would be e to the x, and the derivative at 2 would just be e squared. And this would be the answer if you simplified this limit, because this limit really just means take the derivative and plug in 2. For problem number 3 here, we have a little bit of a different situation. You're going to notice that now we have x approaching 3, and this is going to be the clue that this is going to be the definition of a derivative is that it's x approaching 3, and on the bottom it says x minus 3. So if we look at the way that this formula right here is set up, it's going to be x approaches a, and the bottom is going to be x minus a. And those two things kind of together tell me that this is probably a derivative. So that means that the beginning here is just f of x, not f of x plus h. This is the only special formula that doesn't use f of x plus h at the beginning. It's just f of x. What that means is it's super easy to find f of x, because it's just x minus 1 squared. Now, the specific number we're trying to plug in is also super easy to find here, because it's just whatever x is approaching, which in this case is 3. If I want to find the derivative here, my derivative would just be, I'm going to use chain rule. So I would take the derivative of the outside and then take the derivative of the inside, which is just 1. And then I would plug in my number 3. So I would get 2 times 2, which is 4, and that would be the simplified answer for this limit. For problem F here, again, my clue that this is going to be the limit definition of the derivative is that x is approaching -2 and that this is x minus -2. And that means that the beginning function here is just your f of x function. So in this case, f of x is equal to the cube root of x minus 6. And the specific x value I'm trying to use here is going to be -2, which means my derivative is going to be, now remember, cube root is really a 1/3 power. So 1/3 times x minus 6 to the -2/3 power times the derivative of the inside, which is just 1. And then I would plug in my -2, which is 1/3 times -8 to the -2/3 power. Now that really means 1/3 times 1 over -8 to the 2/3 power. I'm going to do this in 2 steps. The cube root of -8 is -2, and when you square it, you get 4. So your final answer here would be 1 over 12. And that would be the answer if you simplified this limit, because that really means the derivative. For part G, again, x is approaching 5, and the denominator here says x minus 5, kind of tells me this is going to be the derivative. So f of x here would be the natural log function. My x value that I'm trying to use to evaluate would be 5, which means my derivative would be f prime of x is equal to 1 over x. So f prime of 5 would just be 1 over 5. And that would be the answer to this limit. And last but not least, for part H here, again, my clue that this is going to be the definition of the derivative is that I have x approaching 0. I have x minus 0 here. So my f of x function would just be e to the x. And my x is going to be 0, which means f prime of x would be e to the x. And so f prime of 0 would be e to the 0, which is just 1. And that's the answer for this limit. All right, that is going to be it for today. We do have a couple multiple choice questions, and so these are examples of questions you might encounter. We will do these as a warm-up in class tomorrow. Thank you guys so much for watching, and I hope that you have a great day, and I will see you in class for some practice.